Yeah, it's not really something, I don't think it's like extremely hard. Sequences and series, it's not really hard, it's just different. So you got to think differently about it. Really focus today on these concepts of what these mean, and what it means for this to converge, what it means for this to converge or diverge. Because today will lay the groundwork for the rest of the semester. If you get a good foundation laid today, the rest of the class, I don't think will be that hard for you, okay? So we're going to jump right into it unless anybody has any questions first. I will say that this idea of sequences and series is used a lot in Math 80. So if you're taking Math 80 next semester, you're going to see this show up again. There are actually quite a bit of applications of it. We're not going to really go through many of them in this class. However, you need to lay that foundation so you can use them for applications in the future, if that makes sense. Okay? So, start off. First, what is a sequence? It's just an ordered list of numbers. Let's write out some specific examples. You could have, and I want you to focus in on the fact that it says ordered, right? So, one example might be something like this: -1/2, 0, 1, 3.5, 10, and then I could have something like this, say 1, 4, 7, 10, ... This right here is what we call a finite sequence, where if that's a finite sequence, how do you think we would define the next one? Infinite sequence, because this one says that it goes on and on. So this is an infinite sequence. Finite versus infinite. Do something real quick. See if this helps. All right, any questions so far? How many terms are in this? The first sequence, a finite sequence? There's 4 terms. There's some set number of terms. Finite sequence, there are set number of terms. Whereas how many terms are in an infinite sequence? Yeah, there's an infinite number of terms. Okay. Oh, this one had, I think I had a 1 here initially. So the first, well, there was another term here too. It disappeared on me. It was 0. So this right here would be the first term, second term, third term, fourth term, fifth term. So there's actually 5 terms in this one. This again, first term, second term, third term, fourth term, all the way out to an infinite number of terms. A lot of times we label a sequence like this. We'll call it like A sub n. A sub n. Okay. Yeah. Now, does the first sequence appear to have any sort of pattern to it? No, I don't think so. Does the second term have a pattern?
Yeah.
Yeah, what's the pattern?
It adds 3 to each one.
Yeah, you add 3 to each one. Everybody all right with that? Okay. So we could even come up with formulas for sequences. This one doesn't have a pattern. But this one, we could come up with a pattern for. For example, how could we define a sub n? Anybody have any ideas? What are we doing each time? Adding 3. So the first term is 1, and then we add 3 to it. How many times? Or what can we multiply by 3 to make it 1 on the first term?
0.
0. And this would be when n equals 1. So if we want it to be added, if we don't want to add 3 the first time, then we can multiply this by n minus 1. So that would mean that the first term, this would be 1 minus 1, which is 0. 3 times 0 is 0, you just get 1. But then on the second term, this would be 2 minus 1 is 1 times 3. You'd add 4 to it. On the third term, we would add 3 twice. And on the fourth term, we would add 3 times and so on. Does that make sense? Okay? So you could come up with a formula here if there is some sort of pattern to it. This one is actually what we call an arithmetic sequence. An arithmetic sequence is one where we add a constant each time. We will learn later today about something called a geometric sequence. In fact, depending on where you took Algebra 2 or Intermediate Algebra, you may have even studied arithmetic and geometric sequences before. Does that sound familiar to anybody? Yeah? Okay. All right. So I have a little note here. As I said, sequences can be infinite or finite. We're going to deal with infinite sequences. And then another little note, sequences don't have to start with 1. They could. I chose to start this one with 1. However, this one didn't start with 1. It doesn't have to do that way. That also means that if I define a term, if I define these as like this is A1, A2, A3, A4, and so on. In other words, the first term, second term, third term, fourth term. You could choose to skip the first couple terms in a sequence and start, say, with that one. So let's just work with this a little bit. Here's some formulas. This is another way sequences can be written. This is an infinite sequence because there are n starts at 1 and goes to infinity. So there n could be an infinite number of terms. And we could write out what they're going to be. So if we do that, the first term, we're going to plug in 1. So we would have 1 plus 1 is 2. Over 1 squared is 1. So the first term is 2. What would the second term be? 3 over 4. Everybody all right with what I'm doing here? Third term, you add 1 to it, you get 4 over 9. Next one, 5 over 16. Next one, 6 over 25. And do we stop here, or is there only 5 terms? Infinite number of terms, right? So, dot, dot, dot. Okay. Everybody all right with that? Okay. All right. You guys try B. Write out the first 5 terms, please. All right. Now notice that we're starting here with not n equals 1. We start with n equals 0. So that means for the first term we're plugging in 0. Remember, we sit up above here. We sit up above that we do not have to start with n equals 1. You could start with any n that you want. Okay? So, Gabby, what'd you get for the first term? Is that right? Because 2 to the 0 is...
I didn't see that part.
Yeah. 2 to the 0 is 1, right? Okay, that's all right. Elijah, what'd you get for the second one? Positive 1/2. Is that all right? Okay, Jaime, what'd you get for the third term? Negative 1/4. Fourth term, Kim, what'd you get?
I'm working. I'm working on it.
Okay, Stefan? 1/8. And Rose, what about the last one? Did you get that one yet?
Not yet.
Okay. Gabby, did you get this one? What?
I didn't see the power at the end of the bottom.
Okay. Sierra? Negative 1/16. All right, so good. And then it keeps going, dot, dot, dot. This is, remember, it's an infinite sequence. There's an infinite number of terms. Now, what's one thing we notice about this sequence that's different than the last one? Elijah? Okay. Each time it's changing by, it's being multiplied by 1/2, right? 1 times... Well, yeah, it's a negative 1/2. Yeah, each time it's changing by a factor of 1/2, and the signs are also alternating, right? Positive, negative, positive, negative, positive, negative. This is what we call an alternating sequence. This is an alternating sequence. And we call it alternating because what alternates? Yes, the signs alternate. So this is an alternating sequence. The signs alternate. Okay? Now, these two, the formula is given, and we could come up with the terms of it. I could also ask you to do something like find the formula. Here the formula is given, find the terms. How about we go opposite? Notice again that the terms are alternating. Now, what in this formula made the terms alternate? A negative 1. Yeah, so when you have this sort of action, negative 1 to the n plus 1, that makes it alternate. And then the 2 to the n is what gave us the factor of 1/2, right?
Mm-hmm.
Okay. Now, can anything, actually, yeah, so we'll stay with that. See, take like a minute or so, see if you can play around, like see if you can come up with a formula much like this to represent this sequence. And if you think you have a formula, try it with a few ends and see if it works out. You may have to adjust parts of it. Play around, see if you can come up with a formula. Because we may have to do this sometimes. And I would like to think of this, this is a typo in the notes, I believe. I would like to think of this as an infinite sequence as well. So, dot, dot, dot. It's an infinite sequence. So, what is our formula that we can put in brackets there?
Also, it's 4.
And you need the first, one thing that's different about this one is you need the first term to be positive, right? My answer, I started with n equals 1, but you can do whatever you wanted. But I did start with n equals 1 going to infinity. Yep, that'll work. Well, so your original one would be so what is n that you started?
I started at 0.
Yeah.
Okay, so
Yeah.
okay.
It does not have to start with n equals 1. It could start with n equals 0. It could start wherever you want. It really has an effect on what your exponent is. Anybody have it? They want to check their answer? So it's not times n, it would be raised to the n power. It's times n, you're just going to multiply it by 1 or by 2 or by 3 or 4. And then the notation, we usually don't write it like this.
I don't know. I have a numerator.
Kind of like the notation.
I have a numerator.
It would be negative 2/3 to the n. Start at 0 if you do it that way. That would work. When n equals 1, this becomes 0 and 0. You can use the power of 1.
Yeah, I got it.
All right, so the answer that I came up with was -2/3 to the n minus 1. But some of you also had this answer as well. You had -2/3 to the n, and you started n at 0 instead of at 1, which is fine. The key is you need the first term to be 1. And the only way we're going to get 1 is if the power is 0. So if you start in at 1, then the first term needs to be 0. And when you plug in 1, 1 minus 1 is 0. Here, if you start with n equals 0, you can just let your power be 0. Because when you plug in 0, you're going to get 0. See how they're the same thing? Just depends on where you start in. Anybody have any questions? Anybody have any questions? Okay. Not so far? Okay, let's keep moving. If I move down, I say we're also going to be interested in whether or not a sequence converges to a particular value. A graph can be helpful with this. So let's find the first few terms of this sequence. All right, so a sub n is equal to, if I start with 1, this is going to be 2 for the first term. We actually already did this, right? We did it above. What do we have? 2 3/4, 4/9, 5/16, 6/25. We did it up above, ... All right. If we put this on a graph, we can treat it much like we do a function. Could we graph a sub n equals n plus 1 over n squared? Could we graph that? Yeah, you could graph it. Now, the difference is that a function, there's an infinite number of values for what n can be. Or if this was like f of x, if we had a function f of x equals x plus 1 over x squared, how many different values of x are there? There's an infinite number, and they could be decimals, they could be whole numbers. Whereas with a function, or with a sequence, the n's have to be whole numbers, right? And they usually start at 0 or 1. They're not going to be negative values. So if we look at a graph of this, let's just sketch. We just don't talk about the negative first term or the negative second term in a sequence. It usually starts from 0 or 1 or 2. We don't have negative terms.
Okay.
Yeah. So if we were to graph this, we're not going to have a smooth curve. We're going to have points for each value. So the first term, this is our y value. This would be our x-axis. So for the first term, we'd have a point at 2, and then the second term, we'd have a point at 3/4, which is going to be right about there, and then the third term, we'd be at 4/9, which is just under 1/2, and then the fourth term, we'd be at 5/16, which is even lower, and this would be 1, 2, 3, 4, 1, 2. Now, if we were to think about this now as n approaches infinity, is there a value that just from the graph it looks like this sequence of terms is approaching? Yeah. Does it look like it's approaching 0?
Mm-hmm.
Yeah, I would say so. Absolutely. It does look like it's approaching 0. And so the way we're going to find limits is much like how we found limits with functions. Okay? So the way we found limits with functions, especially when we had infinite limits, If we had something like this, we would divide by the highest power in the denominator. You remember those? Okay. So we can do the same thing here. If we wanted to actually find this limit, we could talk about doing something like this. So we could take the limit of a sub n as n approaches infinity. So the notation would look like this. And we could rewrite this then. If we divided everything by n squared, this would be 1 over n plus 1 over n squared. And then n squared over n squared is 1. You guys remember doing this? Yeah. You can, but notation-wise, and we will use L'Hopital as another example. Notation-wise, you got to do a little bit more because you can only apply L'Hopital's rule to functions. So we need to talk about a theorem first before we can do that. But yeah. Now, as n approaches infinity, what are these two terms in the numerator both going to approach? They're both going to approach 0. So basically we get, what just happened? That was really bizarre. Oh. All right, so wow. What page are we on? 10. Where? So, yeah, this is when technology fails you. All right, so but we get 0 plus 0 over 1, which is 0. And does that match what we suspected from the graph?
Yes.
Yeah. So looking over here at question number 2, what does it mean for a sequence to be convergent? As the number of terms approaches infinity, the values of those terms must approach not 0, just some value. In this case it was 0, but as long as the number of terms approaches infinity, or as n approaches infinity, if the terms in the sequence approach one number, that means the limit exists. Or that means that the sequence is, what do we call it? Convergent. And we kind of talked about this. Remember when we did improper integrals? The same concept. With improper integrals, if we took an integral and we got that the integral was equal to a value, we said it converged. But if it went to infinity, we said it diverged. So in this case, if the limit goes to, if you take the limit as you approach infinity and you get some value, we can say that the limit, or that the sequence, not the limit, we can say that the sequence does what? Converges. And all we're saying is that the values of the sequence are converging towards one value. So it could be, if I had a picture like this, 1, 2, 3, and I had the terms looking like this, we could say in this case, the sequence is converging not to 0, but it's converging to 3. Does that make sense? Okay? So it's just as n goes to infinity, the terms approach some value. The value of the terms approaches some value. So are we all right? Does anybody have any questions about these first two concepts? Eddie?
Well, probably not about the concept. Well, I guess so. So when it approaches that value, it converges. Can it pass the value and come back to it? It's kind of like with the.
Yep. And we have something like this too. could be that it looks like this.
Yeah, so really bad. Like,
Yep.
the horizontal
Mm-hmm.
asymptotic
Yeah,
theory,
yeah,
that concept.
it's that idea of a horizontal asymptote. Except the difference is before we had a smooth curve. But we don't have a smooth curve anymore because we're not taking every single value. We're only taking the values at 1, 2, 3, 4. So we're not going to have this smooth curve. We're just going to have the points. But can you see how the concept is still the same? Same concept.
All right. Any other questions? That was a good question. All right. Let's look at the definition then of the limit. It says we say that a limit of a sequence equals L if we can make the terms as close to L as we like by taking n sufficiently large. Sufficiently large means we're just letting n approach infinity. If that limit exists, like that last one we just did, if that limit exists, then we say the limit or the sequence does what? Converges. If it doesn't exist, then we say the sequence diverges or is divergent. All right? All right? So one of the ways you can find a limit is by using this theorem, and we're going to use this whenever we use L'Hopital's rule. So notice what it says. It says that if we have some function, and the limit of that function approaches L, and for that function f, if instead of applying it for all x's, you only apply it for the integers n, and that f of n is equal to your sequence, then we can say that the limit of a sub n is also equal to L. In other words, if you take the limit of the function, you get L, and that function models the same thing as the sequence, then whatever limit you get for the function is also the limit for the sequence. That's all it's saying. In other words, if I take the limit for a function of a smooth curve that goes through a point, a smooth curve, and that function has a limit, and that function is the same thing as the sequence, then that sequence will also approach that same L. That's all it's saying. Questions about that? Okay, limit laws that we had before still apply. We can, if we have convergent series and we add them together, we can distribute the addition of them. We can do all these things. I don't want to talk about them in detail right now. We may mention them at some point as we're doing examples. We talked about the Squeeze Theorem very briefly before. It means if you have a convergent sequence C, where C goes towards some value, and A goes towards some value, and there's another sequence B that's sandwiched between those two. In other words, all the values of B are between A and N. If A and N both go towards the same limit, then B of N also must go towards that same limit. It's the Squeeze Theorem. B of N is between A and C both go towards L, then B must also go towards L. Going quickly through these because these are review. Let's look at a different type of sequence. So this is an alternating one. How do we know it's alternating? Because the negative 1 to the n. Anytime we have that negative 1 to the n, it's going to be alternating. Now, I want to show you a new thing you can do with your calculator. This is a different mode. Recently we've talked about parametric mode. We've talked about polar mode. Well, there's also a sequence mode.
It's amazing.
You've done it?
I don't know.
Yeah. So open up your calculator, if you will. And if you go to mode, and change it to sequence, and then go to your y equals, you're going to put it under the use of n. So this is what the sequence is. So in this case, our sequence is -1. And notice when you push the X button, notice what it gives now. Not a X, not a T, not a theta, but it gives you an n. Because we're defining sequences now in terms of n. And then we want to divide that by n. And if you hit graph, it gives you dots. Now, you can kind of see them up here. Notice they're kind of bouncing around here. I'm not getting a lot of them because of where my window is. What should I maybe make bigger? Do I even need all this negative space over here? No. So we can have x min go from, say, 0 to, how about 10? And I don't think we need that big of y values either. So we could go from like -3 to 3. Try that graph. And notice what's happening. It goes from here to here to here to here to here to here. And you can even hit the trace button. If you hit the trace button, it'll bounce around on these. So that shows you that the first term is at -1. And you hit the right arrow and it goes to 1/2. And then it goes to -1/3, +1/4, -1/5, +1/6, -1/7, and on and on. You see how that works? Anybody have any questions? Okay, so we could see that a sub n is equal to the first term is -1, then we go to +1/2, -1/3, +1/4, -1/5, and so on. Now, looking at that graph, this is basically what we saw in the calculator, something like this. Is that sequence converging? It is hopping back and forth, but is it converging?
Yes.
Yeah. What's it converging to?
0.
0. Now there's a nice theorem that's right here, and it says that if you have a sequence and you take its absolute value, if it's an alternating sequence, so you have this -1 type thing, you take its absolute value, and that sequence, its limit goes to 0, then the alternating version also has to go to 0. In other words, it doesn't matter if these terms are hopping back and forth, positive to negative, as long as they're getting smaller, as long as they're approaching 0, the alternating will also approach 0. It will just approach 0 from the positive, then to the negative, the positive, and the negative. Does that concept make sense? Okay? So we can use that in this case, because this theorem, this says then that if we were to take the limit as n approached infinity of the absolute value of -1 to the n over n, when I take the absolute value, that makes this limit equal to the limit as n approaches infinity of 1 over n. And we can see from the graph of that this limit is approaching 0. So because that one approaches 0, that means that this is also converging to 0. Yeah.
So that rule is only applied for this one as well?
Yeah. So it only works when the absolute value gives you 0. If the absolute value gives you something else, no bueno. It doesn't help us. Only when it's approaching 0. Okay? Any other questions? Yeah. Kind of to answer your question, Michelle, what if you had something like this, where maybe this is at 2 and this is at -2, and they were alternating, but they were alternating like this. In other words, this one's approaching 2, this one's approaching -2. They're alternating, but they're not approaching the same value. The only way they can be approaching the same value is if they're approaching 0. Any other questions? Okay, I think, let me see what I got next here. I think we're just about ready for a break, but yeah, let's go ahead and do these after the break. So 8:58, let's come back at 9:08. 9:08. Take the limit of 3n squared minus 1 over 10n plus 5n squared. And how am I going to evaluate this limit? How am I going to evaluate it? Yeah, Elijah. Divide by the highest power of n where? On the denominator. So only in the denominator. So what's that power going to be? Yep, so if we divide everything by n squared, if we divide by n squared, we're going to get, on the top, we're going to get 3 minus 1 over n squared over 10 over n plus 5. And now can I plug in infinity?
Yes.
And what do we get? 3/5. So is the sequence, as n approaches infinity, is the sequence approaching a value? So we can say the sequence converges. So a sub n converges. Okay, any ideas for the next one? L'Hopital's, yeah, because if you plug infinity, now, but I can only apply L'Hopital's to a function. So what we have to do is if, we can say something like this, if f of x, so some function of x is equal to e to the 2x over x, then the limit of that, the limit as not n approaches infinity, but x approaches infinity, of e to the 2x over x, what is that going to approach if you plug in infinity? What does the top approach? E to the infinity, which is infinity. And what does the bottom approach? If I have infinity over infinity, we can use L'Hopital. So we put our little h here, you guys remember this, and then we take the limit as x approaches infinity. And what do we do with this? Who remembers how we take L'Hopital with somebody? Ken? The derivative. So what's the derivative of the top? E to the 2x times 2. Why do we need the times 2? Chain rule. And then on the bottom, we get 1. Now what do I get if I plug in infinity? Infinity over 1, which is infinity. Yeah. So remember there was that theorem we talked about in the last page. I'm not going to scroll back to it, but there was that theorem that said that if we take the limit of the function, and the function is equivalent to the sequence, and the limit of the function converges, that means the sequence also converges. So we can say a sub n equal to e to the 2n over n diverges. Okay, any questions about that one? Yeah. Yeah, you should do, if you're using L'Hopital's, you should do it in terms of x. Yeah, whenever you have to use L'Hopital's. Because we can only apply L'Hopital's to functions. We can't apply it to sequences. But there's that theorem that we just talked about. Okay? Any other questions? Okay, this one we already did above, right? We already did this above. And what did that one do? Yeah, the limit of, that's how we did it, the limit of the absolute value, right, because it was an alternating series. If we took the absolute value, this limit approached 0. And because the absolute value approaches 0, then the limit as n approaches infinity of -1 to the n over n without the absolute value also must approach 0. We can only apply that theorem, though, if this absolute value approaches 0. But some other value it doesn't work, right? So does it converge or diverge? Converge. The first one converged, the second example diverged, and then this third example converges. All right? And then we have D. What do you think about D? D's a little bit different still. Can we apply that example we just did, C, to D? What does the graph of this thing look like if we were to graph it? What's the first term? What's A? First term is 1. What's the second term? Next term? What do you think? It's going from 1 to -1 to 1 to -1. Is this diverging or converging? Think back to our limit. If we take the limit of the sequence and the limit exists, approaches some L, then we say the sequence converges. Otherwise, if it approaches infinity or does not exist, we say the sequence diverges. Does this limit exist? No. It's hopping back and forth, jumping. So in this case, the limit of -1 to the n as n approaches infinity does not exist. So A sub n diverges. Okay. We got some terminology here. These are pretty basic terminology. If we increase our sequence, the terms in the sequence, so we go from the first term to the next term. If the first term is n, the next one's n plus 1. If the next term is bigger than the term before it, this is saying the next term is bigger than the one before it, we're saying the sequence is increasing. And now if the flip side is true, if the next term is smaller than the term before it, then we say the sequence is decreasing. If it is increasing or decreasing, we say it's monotonic. Okay, it's just a terminology. If there's some bound on the sequence, we say that it is bounded above. If there exists some m such that all the terms are less than that m. Okay? So if there's some value where every term in the sequence is less than that value, we say that it's bounded above by that value. If there's some value where every term in the sequence is above that or greater than that, we say it's bounded below. And then a sequence is bounded if it's bounded above and below. So take that last example we just did. Look at this one. The terms went from -1 to 1, -1 to 1, -1 to 1. What's the upward bound on that sequence? 1. What's the bound below? -1. So it is a bounded sequence. It's bounded below by -1, above by 1. Simple terminology, I think. Any questions about that? Okay, now what if we wanted to tell if a sequence was increasing or decreasing? What's a great tool that we learned in Math 50 for telling that? Not the second derivative, first derivative. First derivative tells if it's increasing or decreasing, right? So what if we let f of n equal negative n squared? Then what is f prime of n? Negative 2n. All right, simple derivative. Now we're considering n's that are greater than or equal to 1, or if n is greater than or equal to 1, that's most of the time we start sequences at 1 and then we go on, right? If n is greater than or equal to 1, what can we say about f prime? Yeah. Think about it. If you plug any positive number in here for n, it's going to be a positive number times negative 2. This is always going to be less than 0. So a sub n, if it's less than 0, a sub n is decreasing for n greater than or equal to 1. Okay. Any questions about that one? Does that make sense? Okay. Okay. What about this one? Negative 1 to the n plus 1. We already talked about that one. Is it increasing or decreasing? That was the one that was hopping back and forth. We already verbally talked about it, right? This is negative 1 to 1, negative 1 to 1. It's not increasing or decreasing because it's hopping back and forth. However, it was bounded, right? It was bounded. It's bounded above and below, and if it's bounded above and below, we say it is a bounded sequence. So this one is not increasing or decreasing. And it is bounded below by negative 1 and above by positive 1. So it's a bounded sequence. Okay. Any questions? I'm not going to do all of these because I want to make sure we get to the next section. There is one down here at the bottom, though, that talks about recursive sequences, and I want to make sure we do that example. So go to the very bottom of the page, and you see that some sequences are defined recursively. That means that it depends on the terms before it. So a very famous one is the Fibonacci sequence. Anybody ever heard of that one? Fibonacci sequence is defined by previous terms. Here is an example of a recursive sequence. It will usually give you the first few terms, and then it will define subsequent terms by the previous terms. So this one says that if your first term is 1 and your second term is 1, then each term after that is defined by adding the two previous terms. Okay? So a sub n equals the term before added to the term before that. So we could write the sequence like this. The first term is 1, second term is 1. The next term is formed by adding the two previous ones. So 1 plus 1 is 2. The next term is formed by adding the ones before that. 1 plus 2 is 3. The next one is formed by adding 2 plus 3, which is 5. What's the next sequence term going to be? 8, 13, ... This is called, this is what type of a sequence? It's a recursive sequence, and specifically, this is the Fibonacci sequence. But there's many different recursive sequences. This is Fibonacci is just one example. Okay?
How often do you see that?
Not that often. If you take Math 160, you'll see it. No, it's not something we see a whole lot, but we're just kind of introducing this concept of sequences, so that's something we put in there. Now, 11.2, we're now going to move on to series, which is a different concept. So, the concept for this one is that you have a piece of paper. You have a piece of paper, say square or rectangular sheet of paper. Yeah, it says 1 foot by 1 foot, right? All right, so I'm gonna simulate this with this piece of paper. About 1 foot by 1 foot. It says let the sequence A of n be the area that results when we fold the paper in half. So the first term in the sequence is the area that we get of this. It's 1 by 1. So what's its area? 1. So let's write this down. So a sub n, the first term is 1. That's the area of this first sheet of paper. Now if I fold it in half, this dimension is still 1, but this dimension is now 1/2. So the area would be 1/2 times 1, which is 1/2. Okay, if I fold it in half again, what are the dimensions now? 1/2 by 1/2, so that area is 1/4. If I fold it in half again, this dimension is still 1/2, but this is now half of 1/2, which is 1/4. 1/2 times 1/4 is 1/8. And can you see where this pattern's going? So this is 1/8. What's the next one going to be? 1/16, and so on. All right. So this is so far. It's just what we did last class or last section, right? 11.1. We defined a sequence. But now, what we are going to define is what we call a partial sum. And all a partial sum is exactly what the words sound like. A sum means that you do what with things? You add them. And partial means that we're not adding up all these terms, we're adding up part of them or some of them. So, if I take S1, that means we're just taking the sum of the first term, which is easy. What's the sum of the first term? 1. Okay, so I take the first term is just 1. Now the second term, or the second partial sum, means to add up the first two terms. So this would be 1 plus 1/2, which is 3/2. Okay. We all right with that? Third term means the third partial sum means to add up the first 3 terms. So we're talking about 1 plus 1/2 plus 1/4, which is 7/4. And then the last one would be we add up how many terms? The first 4 terms. So 1 plus 1/2 plus 1/4 plus 1/8. And what does that come out to? That's, yeah, 15/8. Okay? So, and then, I mean, could we keep going? We can find S5, S6, and so on. So the question is, that is posed here, is to make a conjecture about what happens to the limit of this sequence of partial sums. If I let the partial sums approach infinity, so if I take the sum of an infinite number of terms, is it going to approach some value? Okay? So in other words, what we're talking about is thinking about what would be the limit as n approaches infinity of S of n what is that equal to? In other words, is this answer and this answer and this answer and this answer is stay. No, I got that there. Is or let me write it this way. Are these values 1 3/2, 7/4, and 15/8? Oh, still approaching it. Are these values, the partial sums, are these approaching some value? Not the terms of the sequence, but these terms. Are these terms approaching some value? Maybe they might be approaching 2. That's the question that the rest of the class is going to be focused on. Now, if that limit, if you take the partial sums and the partial sums, the sequence of partial sums approaches some value, then we say that and what this is called a series. The series converges. It's not a sequence anymore. So let's come down here a little bit and look at our definitions here, now that we've kind of introduced this concept. If I can get it to go down. Come on. There we go. All right. So we've already established that if we have a set, this right here, this set of numbers is called a what? No, a sequence. Now, if we add up all those terms, and how many terms are there? Infinite number of terms. Remember, we're talking about infinite sequences. If we add up all those infinite number of terms, the notation, we could use this summation notation. This right here, the sum of all these numbers, is called a infinite series. So this right here, if you add up all the terms in a sequence, that is called an infinite series. Okay. Now, and then we just talked about this idea of partial sums. So the first partial sum just adds the first term. Second partial sum adds the first 2. Third partial sum adds the first 3, and so on, all the way down. If these partial sums, if you take their limit of the partial sums, so if these sums tend towards some value, some L, and that limit exists, if the limit of that approaches some L, then we say that this series converges. In other words, all these terms are not continuing to just go on and on and on and on and on. They're actually adding up to some sum. And you can have that happen. If you add up, it can be that if you add up an infinite number of terms, they all add up to one number. If they all add up to one number, it converges. However, if you just keep adding and adding and adding, for example, if this was my sequence, if I had this sequence, let's do the arithmetic sequence, or arithmetic sequence that I first put up, my first example. I think it went 1, 4, 7, 10, 13, ... Each time you're adding 3, right? If I add up all these terms, and how many terms are there here? Infinite number. If I just keep adding all the terms together, is that sum of all these numbers going to approach some value, or is it just going to keep getting bigger and bigger and bigger and bigger? Bigger and bigger and bigger. So the sum of these terms is called a series. Series is equal to the sum of those terms. It's equal to 1 plus 4 plus 7 plus 10 plus 13 plus ... This is an infinite series. So this infinite series, the sum of all the terms of the sequence, we would say not that it converges, we would say that it diverges. Because that, if you take the sum, so the first sum is 1, the second partial sum is 5, the third partial sum is 12. If you add the first 4 terms, you get 22. If you keep looking at the partial sums, it goes 1, 5, 12, 22. Are the partial sums approaching some value? No, they're just getting what? Bigger and bigger and bigger. So we can't say that this series converges. What would have to happen with these terms? Do anybody have any ideas about what would have to happen with these terms if we wanted it to add up to something? They could alternate. That could be an option, but what's the main problem with this one? Why it's never going to add up to something? These terms keep getting bigger and bigger. So what might you think might have to be true about these terms?
Well, also it has to stop at some point, right?
No, it doesn't have to stop. They keep going, yeah. They have to be smaller, right? Like maybe the fractions. Like if you added, well, we're going to look at some here in a second. I'm not going to throw any out there. But it does turn out that if you add some terms, it will converge. In other words, even if you add up an infinite number of them, they will actually add up to some value. They will converge towards some value. They won't diverge. Does that make sense? Okay. Let me give you a real quick example. And I like this example here. So what if I had, let's say 2 to the n. If I were to graph 2 to the n, that's an exponential function. Everybody all right with that? Mm-hmm. So the first term is going to be 2, the second term is going to be 4. Now what are these terms going to do? It's going to be the same issue we had with the last one, right? They're just going to go to infinity. But what if we had 1/2 to the n? 1/2 to the n, the graph of that looks like what? The first term would be 1/2, the next term is going to be 1/4, the next term is going to be, what does it look like this is doing? going down. So the question is, yeah, they're getting smaller and smaller. The question is, if I take 1/2 and I add it to 1/4 and add it to 1/8 and so on, is that equal to some L? If you add up all the terms. Because if it is, then the sequence converges, right? If that's true, then this converges. Now, these two examples are actually two specific examples of a certain type of series called a geometric series. And it can be shown, it can be proved that for a geometric series, my battery is nearing the end of its useful life. How about that? That's why
That's not last very long.
I didn't replace it last time. I forgot.
You have more quadruple A batteries?
I do, but they're in my office. You guys mind if I run over and get that real quick?
Nope.
Take a 1-minute break.
Take your time. Dude.
So I'm not even gonna do it.
But it's like, it feels, I feel like it's not even that hard.
I know, I feel like it's so basic, but yeah,
But
I'm stressing for
you
the
guys
fact
do-
that it's Tuesday.
No, he's not. Why would he?
Yeah, I don't need to do it.
He's gonna make it complex, yeah, but it's gonna be the same concept.
Yeah, as long as he's doing it.
Yeah. Oh, you suck. I bet you that one. Are you sore from that little run?
No, like, my legs literally is.
He's been squatting you.
Yeah. I'm getting stop.
We used to go into like those Okay, should be good now. Let there be battery. All right. Okay, so if the sequence of partial sums diverges, then the series also diverges. If we add up all the terms, it diverges. So we have a series here. We have a series 1 over n times n plus 1, and we're asking, is this series convergent? In other words, if we add up all the terms, do they tend towards one value, or do they explode on us? Now, just looking at it, what do you guys think? Just looking at it. Looks like it might go towards one value. Looks like it might go towards one value. Think about that for a second. How do we know? Well, actually, the first question, how do we know it's a series? What makes it a series? Yeah, Michelle. Yeah. So anytime you're adding the terms of a sequence, that makes it a series. Okay? Just like we did in the first example with the paper, what I want you guys to do is write out the first partial sums. So I want you to find, very first thing, just like we just did, please find S1, S2, S3, and S4, okay? Go ahead and just do those real quick on your own. And we will talk about this in a second. You probably want to start with what the sequence, the series looks like. So So what does a sub n look like? That's where I would start. So the first term is 1/2, right? Second term is what? No, it's not. It's never. It's always going to be 1 on the top. 1/6, 1. 3 times 4, 1 12, 1 20th. Oh. These are the terms in the sequence. Yeah. So these are the terms, but the partial sums say that you do what with these terms? Add them up. So S1, just to get you started, S1 is just going to be, you add up the one, yeah, it's not really adding, but. Okay, so you guys do the last 3, yeah?
See that?
Okay, you were doing this.
I jumped the step.
Yeah, I don't.
Okay.
Then I got to be like, wait. If you reset the memory, good.
That works? Yeah. I'm going to show you something beautiful on your calculator here in a second, because I see you guys going to add these. Okay. Huh?
It's like, it's weird. It's like adding 1 each time.
Okay.
I don't know, but I got almost my hand. Is it the same on the 8 board as well? Yeah, he does actually get one.
Yeah. Download it.
Does it work on anything?
It works on PCs, I think. It's because it's a .exe file. Yeah. It's you can find it for free. All right. So when you add up the first 2 terms, what do we get? 2/3. What about when we add up the first 3 terms? Everybody agree with that? 3/4. And then the next one? 4/5. Okay. You add them all up, ... The first 4 terms, you get 4/5. All right, so now, S of n, the sequence of partial sums. What's the first term in that sequence? What's S of 1? 1/2. What's S of 2? 2/3. What's S3? 3/4. What's S4? Equals 4/5. So the question is if I... Oh. The question is, if I add all these up, does this sequence converge, right? Okay. Now, before I get into answering that question, I want to show you how your calculator can do these really, really quick. I actually just figured this out last night. I never did it before, but I was preparing for class today. I was like, there's got to be a way, rather than like doing this by hand. There's got to be a way for your calculator to do this really easily. So let me show you that. I just figured it out last night. It's pretty cool. So go to your calculator, and we're going to go to we're at list. We're going to go to list. I was forgetting for a second where it's at. But so quit, and then go to list, second list, And if you look under math, the first thing we want to do is we want to choose option 5 because we're adding. So we want to do the sum. We want to add up. We want to add up the terms of a sequence, right? Add up the terms of a sequence. And I just remembered we need to actually do the next step before I can finish this. So pause for a second.
Okay, so excited.
So remember last section when we did 11.1, we talked about how we could look at the terms of a sequence and come up with a formula for it. So this first term. This first term was when n was equal to 1. This was 2. This was 3. This was 4. Did we come up with a general formula?
Well, isn't that the general formula right there?
No. This is the formula for the terms of the sequence. We now want to come up with a general formula for the terms of the partial sums. Because we're not trying to tell if this converges, we're trying to tell if the partial sums converge. Because if the partial sums converge, then the sequence, the series converges. So what's the formula? What is happening on the top? Yeah?
I was going to say it's n over n plus 1.
Yeah? I think that's good. N over n plus 1. So the nth term of this sequence is n over n plus 1. Yes? No? Yeah? Uh-huh. Okay, so now let's go back to our calculator. Now that we have an nth sequence, what we can do is, first of all, this part we know the formula. I got ahead of myself. Sorry. I was jumping ahead 2 steps. We can use this formula to figure out these answers. So what's the formula? We want a sequence. So we go, first we do sum, then we go back here to list and go under operations, and notice the 5th option is what? Sequence. So you do sum of a sequence, and then the first thing you do is you give the formula. So we're going to go 1 divided by parentheses n plus 1. Question?
Mine's a little different.
Sequence, you go to list, so you go second list, and then you go to calculate, and it's the option second list, ops, and it's the 5th option.
Okay, I see it.
So the first thing is sequence, sum, then sequence, and then you have to put in your actual sequence. So we're doing this one, 1 over n times n plus 1. Comma, whatever your variable is. In this case it's n. Comma, if you want to add up the first term, which we already know is 1/2, but what if, say, we want to add up the first 2 terms? So we're going to go from n equals 1 to n equals 2, and then you need 2 sets of parentheses at the end. So this is what this is doing. Let's talk through it. It's building a sequence. The sequence is 1, it's this sequence, right? This sequence is 1 over n times n plus 1. And we're going to, for that sequence, we're going to allow n to go from 1 to 2. So how many terms is that going to build us? 2 terms. And then that parentheses is to close the building of the sequence. And then this sum needs another set of parentheses. We're going to add up those 2 terms. So it takes a little bit of work the first time, but once I press enter now, notice what we get? 0.667, and of course you can use the math to fraction button if you don't know that's 2/3. That's what we got here, right? 2/3.
Oh, okay.
Now, the nice thing is you don't have to keep typing that, because you can go up to your previous entry. Some of you can go up and just highlight it and press enter. If you can't highlight it, you just say second entry until you get to that previous one. And then what do I need to change in this one? Just change it to a 3. You change it to a 3, you get
It's more complicated.
0.75. Now, you're going to see in a second, though, why it's nice. Okay? 0.75. Do it again. Change it to a 4. 0.8. 0.8 is 4/5. See how this is going? Any questions? All right. Now let's go back to the series. The series is when we add up all the terms. And we just said on the previous page that a series will converge if the sequence of the partial sums converges. If I add up all these terms, they will add up to a value. They will converge if the sequence of the partial sums converges. So the question is, does this partial sum, does this sequence converge? And we just learned in the last sections how to tell if the sequence converges. How could we tell if this sequence converges? Just take the limit, yeah. This is a sequence. We can tell if a sequence converges by taking its limit as n approaches infinity. If we get a number, it converges. If we get infinity or it doesn't exist, then it diverges. So that's it. Take the limit. Take the limit as n approaches infinity of s of n, which we just figured out the formula for that. What's the limit as n approaches infinity for s of n? N over n plus 1. And how do we find that limit? Divide everything by n. You get 1. You get 1 over 1 plus 1 over n, which is 1. So the limit of partial sums approaches 1. That means that, think about what this says. That says that if you add up the first term, the first 2 terms, the first 3 terms, the first 4 terms, if you add up the first n terms, the limit of the sum of those first n terms is 1. So does the series converge?
Yes.
Yeah, and what does it approach?
1.
1. Now, check this out now. Go back to your calculator and let's use this notation that we've just been using, and let's now change to this part here. Just go second entry. Second, enter, and it gives you your previous entry. So now we're going to do it for n over n plus 1. This is the nth term of our sequence, comma, n. Now how many terms do we want to add up? How many partial sums do we want to add up? Or how many of these terms do we want to add up? How many of these do we want to do? 20?
Yes.
So comma 1, comma 20.
Alright, cool. I figured it out.
No, I didn't want to do that. I'm sorry. I did the wrong one. Go back to this one. I meant the original one to go to 20. So 1 to 20 of the original one. 0.95. And look, what if we change this to 30? What is it going to get closer to? What do you think? What's going to get closer to? .97. You change it to 50. It's adding up the first 50 terms. 0.98. Can you see how what this is doing? The partial sum, the limit of the partial sums, right here, the limit of the partial sums is approaching 1. Therefore, what's the sum of this series if we add up all the terms? If we add up all the terms in the series, it is 1. Because each of these partial sums, if we add them up, are approaching 1. That means the series has to add up to 1. Does it make sense? Sorry about putting in the other sequence. I don't know why I did that. But questions?
Alright, figure this out.
Okay?
The general formula of it?
Yeah, it's coming up with this.
Yeah. I think that's the only thing I'm kind of iffy about.
Well, you're just looking at the... But the good news is most of these we're not going to have to come up with this. This is just an example to explain the idea of how it works.
Okay, which makes sense.
The ones that you're going to be doing in the homework is a geometric series. And it's this idea, but we don't have to actually come up with a formula. There is already a formula that adds it up for you.
Okay, cool.
So check it out.
Yes.
Geometric series. Geometric series. Geometric series have this form. You start with a value, a, and then each subsequent term, you multiply it by r. You multiply it by r twice. You multiply it by r 3 times.
What's R?
R is the common multiple. So, I mean, here's an example right here. The first term is 0.9, and then you multiply each time by 0.1. If that r, whatever the r is, if it is a number, its absolute value is less than 1, it converges. Okay? If r is less than 1, then it's convergent, and its sum, if you add up all the terms, its sum is the first term divided by 1 minus its r.
Okay, that's good.
That's what it adds up to. It does converge, and this is what the series adds to. If its absolute value is greater than 1, it does not converge, it diverges. In other words, if I take the sequence of the partial sums, just like our previous example, if I take S1, S2, S3, those sums, partial sums, are not approaching a number, they are approaching infinity, they diverge. The last example, the sequence of the partial sums approach 1, it converged. So here's this question. For what values of r does a geometric series converge? If the absolute value of r is less than 1. For what values does it diverge? If the absolute value of r is greater than or equal to 1. What is a series? Sum of an
Ordered sequence.
infinite sequence. Sum of an infinite sequence. What does it mean for a series to converge?
It approaches some value.
What approaches some value?
Series.
The sum of the series.
The sum of the series, or this, what I like to say is the sequence of the partial sums. If you take the limit of the sequence of the partial sums, and that is equal to L. So if the partial sums converge to some value, as n approaches infinity, then the series converges. In our previous example, it did converge. Remember, the first one was like 1/2, and then it was 2/3, and then it was, what was the next one? 3/4, and then it was 4/5. These values were approaching 1, right? These values were getting closer and closer to 1. So for that one, this was actually equal to 1. Example. What is R for this example? Or what is R and what is A? A is equal to 0.9 and R is equal to 0.1. Now how do I tell if it's convergent or divergent? R is less than 1. R equals 0.1. 0.1 is less than 1. So it is what? Convergent. If convergent, find its sum. Well, its sum, the sum of n equals 0 to infinity of 0.9 times 0.1 to the n is equal to the first term. What's the first term? 0.9 divided by 1 minus r, which is, what's r? 0.1. Where am I getting this formula from? Right here. If it is convergent, if r is less than 1, then the sum of the series, the sum is a over 1 minus r. A over 1 minus r. 1 minus 0.1 is what? 0.9. So this is 0.9 over 0.9. What does the series add up to? 1. Questions? It's not too bad, right? Anybody have any questions? Okay, how about this one? Give it a little bit different. Is it geometric? Is it multiplied? Actually, let's go back to the last one real quick. If n equals 0, what is the first term in the sequence? 0.1 to the 0 is 1. We have 0.9. If the next term, if n equals 1, 0.1 to the 1 is 0.1, and 0.1 times 9 is 0.09. Next one is 0.009. Next one is 0.0009. Because each time we're multiplying by 0.1, right? Now what happens if I add up all these terms? 0.9 plus 0.09 plus 0.09. What if I add them all up? Can you see why the sum is 1? Because this plus this plus this plus this is basically 0.999999999. Okay? So I could have listed them like this and come up with the fact that, oh, my first term is, my A has to be 0.9, and then how do I get from here to here? How could I figure out that, if I was given this and I wanted to go back to this, how could I figure out that R was 0.1? Divide. You just divide it. You just take this minus that, or divide it. This divided by this. 0.09 divided by... In other words, R is a(n plus 1 divided by a sub n. You take the term divided by its previous one. So in other words, you could take 0.09 divided by 0.9. And what's 0.09 divided by 0.9?
Yeah,
0.1. Yeah? Yeah, okay.
Sorry.
So how could we figure out if this is geometric? Is there a common r that we're multiplying by? What am I multiplying to get from here to here? 2/3? 2 times 2 is 4. 3 times 3 is 9. Does that work for the next one? 2 times 4 is 8. 3 times 9 is 27. Yeah? Okay, so everybody together, what's a equal to? 2/3. A is the first term. What is r equal to? Yes, r is also 2/3 because we're multiplying each term by 2/3. Does it converge or diverge? Converges. Why? R is less than 1, so it converges. And what does it converge to? A over 1 minus r. A is 2/3, and then 1 minus 2/3. 2/3 over 1/3 is equal to what? 2. So this series converges, and it converges to 2. You guys try B real quick. We're almost done. A equals 1 and r equals -1/2, yeah? Agree or disagree? Converge or diverge? Because the absolute value of that is less than 1. So it converges. My pen will write. It converges to 1 over 1 minus what? -1/2. Which is actually 1 plus 1/2, which is 3/2, and 1 over 3/2 is 2/3. Now what if I gave you this sum series? What if I gave you 5 times 2 to the n? Does that converge or diverge? Diverges. Why? R is greater than 1. This diverges because R equals 2, which is greater than 1. Another special case. How about what if I have the sum, what if I have the sum of n equals 1 to infinity? No, we'll skip it. I need to move on. Harmonic series. Any ideas about this one?
This is the one that oscillates.
It doesn't oscillate. So the terms of the sequence are going to be 1, 1/2, 1/3, 1/4, 1/5. The question is, if I add up all these terms, do they add up to a number or do they diverge? Converge or diverge? I mean, it kind of looks like what we've been doing, like it would converge, right? Because they're getting smaller. It turns out that this series, it's called the harmonic series, 1 over n, that this actually diverges. It says right there in the notes, right? We will prove next class, well not next class because we'll be reviewing next class, but we will prove in section 11.3 why this diverges. So anytime you see 1 over n, we call that the harmonic series. It diverges. Does the harmonic series converge or diverge? Diverges. Anytime you see 1 over n. Now, we have one last test, and this is a really easy test. I told you we were going to go late today, so I apologize, but we got to get through this so we stay on track. We're almost done. Test for divergence. This test only tells if a series diverges. It says nothing about whether or not it converges. So if you suspect it might diverge, you could try this out, but it's not going to tell you if it converges. If the test fails, you have to try something else to see if it diverges or if it converges. So look what it says. If a limit of a sequence does not exist, or if the limit is not equal to 0, as in, if we take the limit of that example, the limit as n approaches infinity of n squared over 5n squared plus 4. If we take that limit, what do we get? 1/5. Is this equal to 0?
No.
It's not equal to 0. What does the test for divergence tell us?
If it's divergent.
It tells us that the series, that this is divergent. That's all this test says. What about if it equals 0, though?
You have to find out if it.
Then we have to do more work.
You have to do more work. And that's what the rest of the chapter is going to be about. Chapter 11.3, 11.4, 11.5, 11.6, we're going to learn different tests to tell if it is divergent or convergent. Yeah.
Okay, so if limit does equal 0, does that mean it's definitely not divergent?
It's inconclusive. If the limit equals 0, it's inconclusive. If it doesn't equal 0, it's divergent. What about this one here? Okay, now let's be clear though. This does not say though that the sum is 1/5. It doesn't say that the sum is 1/5. It just says that the series is divergent. And if the series is divergent, does it have a sum? It doesn't. Okay. What about this one? Does that look for like anything we've done? It looks like the harmonic. In fact, this is equal to 1/7 times the sum of n equals 1 to infinity of 1 over n. And 1 over n is divergent. This is the harmonic. So this series is actually divergent as well. So the main thing you're going to be doing in your lab is if it is a geometric series, you're looking at R. If R is bigger than or equal to 1, it converges. If it's less than 1, it diverges. If it looks like the harmonic series, it diverges. And if it's not one of those and you suspect it is divergent, we could try the divergence test, and the way you do the divergence test is you just take the limit of its sequence, and if we get the limit that does not exist, or if we get something that's not equal to 0, that means that the sequence does what? Diverges. If it's equal to 0, inconclusive. We don't know. And this was our longest day of the semester. I apologize.